and delta ij multiplied by phi I with the sum on I equal to 1 to m, the only term that is going to survive is going to be phi j. Okay? Is going to be phi j. So I can say that this is composed with phi j. Okay? This is composed with phi j. Now, what we can see from this, that if you keep in view, for example, this expression of partial x by partial gamma by partial xij, xi equal to 0 is a critical point of it. Size equilibrium xi equal to 0 is critical point. Why? Because all these xi's are going to be 0. So if this is 0, all these xi's are going to be 0. And if all the xi's are going to be 0, this expression will be 0. Psi of 0 will be 0. Then the Fresher derivative of e of psi, this entire term will be 0. I mean, if you carefully think about it, actually. Okay? Or if not, you can also think about this term actually. That if the xi's are 0, this entire term is 0. And this is a linear operator operating on to 0. So this entire term is going to be 0. And and hence this composition is going to be 0. Okay, so what you can see that this xi equal to 0 is a critical point of the map gamma. Okay, this is one of the things that you should get. Now I'm going to use these facts and do something. And maybe before getting into it, let me mention an aside thing. And I'm treating this as an exercise for you. I did one calculation of Fresher derivative of computing the Laplace u plus u minus u cube. Now I'm giving you a simple exercise which says that if you have e of u, okay, which is the integral with respect to the space variable, the gradient of u square by 2 plus u power 4 by 4 minus u square by 2 dx. Okay, so the exercise is to show that if you compute the Fresher derivative of e onto a u and operate it onto a y, okay, if you compute the Fresher derivative of e onto a u and then operate it onto, for example, a point y, then this Fresher derivative is going to be equal to gamma omega, the integral over omega of the space variable, gradient u dot gradient y plus u cube minus u times y dx. Okay, so your task is to take this and show that this is really the Fresher derivative of e of u operated onto some y. And I mean, if you can prove this, then it is also easy to deduce actually. By the way, why I am interested in computing this, because I have to compute this expression and compose it with this and compose it with phi j. Okay? So I have to think about carefully this expression, this entire expression. Because if I have an expression for the Fresher derivative of e of u operated onto y, I can think sensibly about it actually. Now, where y is also from h actually, h2 intersection h1 naught. Now, if this is the case, I can apply the integration by part on this, and if I wish, I can take this Laplace operator on the other side, okay, this gradient on the other side, and this will become gradient operated onto gradient of y, which is going to be minus Laplace y. by integration by parts. So in other words, this dE of u, it is not difficult to see that using integration by parts, you can rewrite this as u dot, or maybe, no, I want to take this gradient operator with u actually, okay, so that I can get my favorite expression. So I can write this as minus Laplace u dot y plus u cube minus u y and dx. And hence you can put it simply that this is going to be minus Laplace u minus u plus u cube times y dx. So this is really the expression for the gradient of E of u. E of u. Okay? The Fresher derivative of E of u. Now, so here's the thing. If I now take a u which is a sum v plus psi, and on that u I operate what do you call a psi. In other words, I can say that let's take this expression as a something v, okay, plus psi. So this is plus psi. So if I take this as u, okay, if I take this as u and compute the gradient of E onto this u, which is this, by the way, I can go even one step ahead. Let me write it explicitly. Okay, so you have to be with me, bear with me. Okay, so it's a pretty involved kind of proof actually. Now we know that for u, if I have something added to what you call equilibrium, in other words, the v is the difference of u minus psi, then I know the description of m of v. In other words, the m of u minus psi, that this is equal to minus Laplace u plus minus Laplace u minus Laplace u minus u plus u cube. This is what is really the expression for it actually. And if this is the case, then I can also write this expression as m of v, where the v is what? U minus psi. U minus psi. Now, if I want to compute dE, the Fresher derivative of E with v, okay, with some v, which is this expression plus psi. So this is like I am calculating the Fresher derivative of E of u. What would be the outcome of it? The outcome of it, so now let me write partial by partial gamma xij. So this first expression is going to be the m, okay, m operated onto v, where the role of v is playing this expression. So this is going to be m of the psi of this sum that goes from I equal to 1 to m xi I phi I. Okay? Because this is equal to m of v, where u is v plus psi. So if I have the Fresher derivative of some u, which is some v plus psi, then and operate it on what you call y, then this would be equal to m of the v, multiplied by y, okay, and it's integral actually. Now what is the playing the role of v? The role of v is played by this expression. So hence I can say that this dE operated onto this is going to be the integral, okay, of this m of what you call psi of v, which is, m of v, which is this expression actually, okay, which is this expression. All right. So now, okay. So now, what I would like to do, on both sides, I want to take the absolute. Okay? And when I'll take the absolute, this can be estimated by the norm of this, the norm of the first quantity, which becomes m of psi of this, as times the norm of this, which is going to be d psi of, okay, sum I equal to 1 to m xi I phi I, the norm of this. And if you wish, you can compute this norm, because d psi is a linear map from L2 to H, so you can consider its operator norm actually, okay, from L2 into H times the norm of phi j, L2 norm of phi j. But I know that phi j's, phi 1, phi 2, they are the bases, orthonormal bases of the kernel of L. So they are orthonormal vectors. So if they are orthonormal vectors, their norm is going to be 1. So if you wish, you can get rid of this actually. If you wish, you can get rid of this. Okay? So what does this shows? This shows that you have this. Now, I know that this is a linear operator, and I'm computing the operator norm. So if I wish, I can give this operator norm, because this indeed belongs to this map, so this operator norm must be finite. So if it is finite, I can say that I can estimate this by some constant, which could be the norm of, what do you call, this operator norm, times the m of psi of this sum that goes from I equal to 1 to m and xi I phi I. This is what that you're going to get actually. I will use for all kind of constants that are going to involve in our upcoming discussion, I'm going to use them C, I'll denote all of them by constant C actually. So if I have to add C into another constant C, I'll again call it C. Okay, so I'll keep on using this constant C again and again actually. So what follows from here is that the partial derivative of the xi j can be estimated by C times of n of, what do you call, this expression. And if this is the case, if every single component of if every single partial derivative for every j, okay, can be estimated by this number, then in fact you can say the entire gradient of xi can be estimated by this C times of norm of C times of, okay, C times of norm of m of psi of sum that goes from I equal to 1 to m xi I phi I, okay, and it's norm. So if each component of it can be estimated, then the gradient of the gamma can also be estimated actually. Okay. Let's make our life a little bit easier. Let's call this expression I equal to 1 to m xi I, phi I, you can treat this as the projection of some v. Okay? So I can treat this as the projection of some vector v onto the kernel of L. Okay? Then I can write this, the gradient of gamma, the gradient of the gamma as a c times of norm of m operated onto some pi v. This is what that you're going to get. And now let me add and subtract. So I want to have an interesting estimate on gradient of gamma, which I can use later in order to deduce our version of inequality. Okay. By the way, the map gamma already satisfies the conditions of Łojasiewicz-Simon inequality. So we have already the Łojasiewicz-Simon inequality for gamma. We have to just wait to use it. So I can do what? M of say pi v, and say add and subtract m of v into this expression, actually m of v plus m of v. So I can, by triangle inequality, I can say that this will become m of pi v minus m of v plus the norm of m of v. Okay? So this is the inequality that we have. Let's call it, say, inequality B actually. So there are some inequalities that we have to keep in our head. Now I'm going to say, I know about the map M, the calligraphic N, that it is Lipschitz actually. So if it is Lipschitz, I want to deduce that M is also Lipschitz, so that I can have an estimate for the gradient of gamma in the terms of the map M. Okay? Now I know the calligraphic N of V is M of V plus pi of V actually. Okay? So I can compute this M of, what do you call, pi of V, or in fact a general expression M of V1 operated on M of V2, I can say that this is going to be, or it can be estimated. So M of V is the difference of these two. So I can estimate, so I can calculate M of V1, which is going to be N of V1 minus pi V1. M of V2 is going to be N of V2 minus pi of V2. Taking their difference and applying triangle inequality, you're going to get N of V1 minus M of V2 plus pi V1 minus pi of V1 minus pi of V2. So this is what that you're going to get. Okay. For N, I already know that it is Lipschitz, so I can estimate this by some constant times norm of V1 minus V2, H norm, okay, plus we know about the orthogonal projections that they satisfy this condition in general, that projection of any vector V and its magnitude is always less than or equal to the magnitude of the same vector actually. Okay? Magnitude is always less than or equal to the magnitude of the same vector. So I can say that this can be estimated by V1 minus V2. So this will become obviously H norm, okay? Obviously H norm. So I can say what? I can say that this is going to be equal to constant C plus 1 times the norm of V1 minus V2, but I'm going to call this constant C plus 1 again the constant same actually C times norm of V1 minus V2. Okay? So what does this show? That M is also Lipschitz. We know that N is Lipschitz in a small neighborhood, then M is also Lipschitz in the small neighborhood. So this is the first conclusion that I would like to have. And now Using this, I want to have an estimate on, for example, this term, the first term. So what it would be? So it will be this. Consider this term. Next, so if I consider psi of pi v minus v, consider this term, then I can say in H, I can say that this is same as psi of pi v minus, I can write this as psi operated onto n of v, okay? Psi operated onto calligraphic n of v, okay? Because psi and n, they are what do you call the inverses of each other locally. So, and on this inequality, if I, for example, now apply the inequality that is what the Lipschitzness of the inequality, or Lipschitzness of psi. So I can say that I can estimate this guy by the norm of pi v, okay, minus n of v, okay. But pi v minus n of v, or pi v minus n of v is really m of v actually. So this is same as the norm of, you know, m of v. Okay, this is same as the norm of m of v. So now we are ready to meet with this term. We are ready to meet with this term. Now, using this inequality and, you know, Lipschitzness of m, using these two, you know, in this, let's see that what you get. Now from B, I can say the gradient of the gamma can be estimated. So what would be the first? So first I can apply the Lipschitzness, and I can say that this is going to be less than or equal to psi of pi v minus v, but for in H obviously, but for this you have estimate that that this is less than or equal to some n of v, okay, some n of v. So if you wish, you can put a constant c here, and you can see that we have some constant c. So this c plus, you already have m of v. So I can say that this guy is less than or equal to c times of m of v plus the norm of m of v. So c plus 1, I can again call it constant c, okay, times the norm of m of v. So I can say that you get an interesting estimate on the map gamma in the terms of m of v. And if you remember, don't forget that your m of v is really Laplace u cube, Laplace u, okay, minus Laplace u, or Laplace u minus u plus plus u minus u cube. Okay, so somehow this is now related with this. Okay, and if you think carefully a little bit about it, this guy, which is Laplace u plus u minus u cube, is bigger than or equal to gradient of gamma. And if you apply, for example, Łojasiewicz inequality, gradient of the gamma is bigger than or equal to the difference of what do you call the increments of gamma. So now I want to calculate what do you call the increments of the gamma. In other words, gamma of xi minus the gamma of 0. And let's see what we get. And so let's move towards that. But before that, let's do one little more calculation. You can see that it's a lot of work. Okay, it's a lot of work. Let's call this equation 1. I'm going to use it again. So let's now take, say, an instant t from 0 to 1. Okay, and let's take a v from w1 of 0. Okay, w1 of 0 is neighborhood of v. I know that psi of pi v is going to be also element in w1 of 0, and if you subtract v, this is also going to be an element in w1 of 0. Okay, so if they are element in w1 of 0, then their convex combination is also going to be an element in w1 of 0. So I can say that, say, v plus t times psi of pi v minus v is also an element in w1 of 0. Okay, keeping in view this fact. So now I would like to calculate an interesting thing. Keeping in view that u is, say, v plus psi. Okay, let's calculate this. And what is this? This is the difference of E of u minus the gamma of xi. This is what I would like to compute. Okay, E of u minus gamma of xi. I mean, if you remember the definition of gamma of xi, that it is E of u minus E of psi of pi v plus psi. Okay, plus psi. This is what the definition of gamma of xi is. And now if I, for example, apply fundamental theorem of calculus with respect to time, I can put these two terms into a single term. So let me write, say, for example, 0 to 1, absolute 0 to 1, E of the derivative with respect to parameter t of E of u plus 1 minus t times psi of pi v, no, E of this, no, E, yes, psi of pi v minus v. Okay, this is what you have. My claim is, and obviously dt, my claim is when you compute this derivative, you should get this. So by fundamental theorem of calculus, this integral will be equal to E of this quantity evaluated at 0 and 1. So when you're going to evaluate this expression at t equal to 1, this term will go away and you're going to get E of u. Okay? And if you evaluate, for example, this term at t equal to 0, so you're going to have 1 minus 0, psi of pi v, so it's going to be u plus psi of v minus v. But the u minus v is psi. So you're going to get, psi v plus psi of pi v plus psi actually, because the u minus v will become psi. So this expression makes sense actually. Okay? So by fundamental theorem of calculus, I can write this expression as this. Now if I compute the differential derivative of it, I'll do a jumps, in some of the following steps. Okay? It's taking a lot of time. So I will leave some of the calculations for you to do for yourself. Okay? What would be the partial the derivative of this? So the derivative of this expression is going to be the Fresher